Welcome to the deep dive. Today, we're jumping into something incredibly small but moving incredibly fast. Micro and nanorobotics.
Yeah, we're talking machines, actual functional machines, built on the scale of microns, maybe even nanometers. Think 10.6 or 10.9 meters.
It's kind of mind-bending. It takes us from Richard Feynman's, 1959 idea about plenty of room at the bottom, and even that old movie Fantastic Voyage.
Right, from sci-fi right into, well, actual labs today.
But here's the first thing you absolutely have to get your head around. Shrinking down a submarine or any normal machine, it just won't work.
Exactly, that's the key. The physics completely changes at that scale. You're in what's called the low Reynolds number world.
Low Reynolds number, meaning...
Viscous forces just dominate everything. Imagine trying to swim not in water, but in something like thick honey or syrup.
Okay, so like swimming through molasses. If you stop moving your arms.
You stop instantly. There's zero coasting, no momentum carries you forward.
So that's the first big tyrant.
Yeah.
Viscosity.
Yeah.
You need constant propulsion, right? No gliding.
Constant, relentless propulsion.
Yep.
And then there's a second tyrant, Brownian motion.
Ah, the random jitters.
Precisely. These tiny bots are just constantly being bombarded by molecules, pushed around randomly because of thermal energy. It's like this chaotic dance.
So the robot has to actively fight that too, just to go in a straight line.
It has to overpower that noise continuously. So, yeah, traditional designs, propellers, things like that, they're useless.
Which leads to the Scallop theorem. You can't just open and close something symmetrically.
Oh, no, you'll just wiggle in place. That's the theorem. You need non-reciprocal motion, something asymmetric, like how a bacterium uses its flagellum, or a fish swims.
So how do they build things that can do that? Especially when they're smaller than a cell.
Well, that's where the ingenuity comes in. One really clever approach is biohybrid systems.
Meaning using actual living cells.
Yeah, basically borrowing nature's motors. Think modal bacteria or even sperm cells. They already have these incredibly efficient propulsion systems built in. You just attach your payload.
Okay, that's smart. But what about building them entirely from scratch?
For that, the big technology is 3D nanoprinting. Specifically, something called two-photon polymerization.
Two-photon polymerization sounds complex.
It lets you sculpt really intricate 3D shapes, like tiny helices or corkscrews with nanoscale precision. You use lasers to harden polymer, like one tiny spot at a time. Essential for making those non-reciprocal shapes needed to be the Scallop theorem.
Okay, structure sorted. What about power? You can't exactly stick a battery on something that small.
No, yeah, definitely not. So for anything inside the body, the leading method by far is external magnetic fields.
Why magnetic fields?
Well, they're fuel-free, totally non-invasive, they can penetrate deep into tissue, and crucially, you get precise real-time control. You can steer them.
And you can even use existing tech, like MRI machines.
Sometimes, yeah. Parts of MRI systems can be adapted, which is a huge advantage.
Okay. And outside of medical uses, you mentioned chemical propulsion.
Right. That often uses Janus particles. Think of a tiny sphere coated half with, say, platinum.
Janus, like the two-faced god.
Exactly. The platinum side reacts with fuel in the environment, like hydrogen peroxide, H2O2, and creates thrust.
Yeah.
Bubbles, basically.
So they're fast.
Very fast. But the fuel, like peroxide, is often toxic, so it's mostly for things like environmental cleanup, not usually inside a living body.
Well, let's talk applications then. In medicine, I read about these PMDM microrobots for inflammatory bowel disease. They sound amazing.
Oh, they are. Really clever design. They're tiny, about 0.2 millimeters wide. You deliver them to the gut.
And then the magnetic field comes in again.
Yes, but here's the cool part. The field makes the individual bots self-assemble into flexible chains, almost like tiny inchworms.
Inchworms, why?
Because that chain shape lets them crawl effectively along the complex, slippery surface of the intestine. They can navigate that terrain much better as a chain than as individual swimmers.
Wow, so they crawl to the inflamed spot, deliver the drug.
Deliver it precisely where needed. And then, importantly, they can be guided back out and retrieved. It's a whole targeted delivery and retrieval system.
That's incredible. Okay, shifting to the environment, these Geox microbots for cleaning up lead.
Yeah, another great example. These have layers. Graphene oxide that grabs the lead, a nickel layer for magnetic steering, and then platinum, again, for that chemical propulsion using hydrogen peroxide fuel.
So they're self-propelled lead magnets.
Pretty much. And the key thing is that because they move around actively, they encounter and capture lead much, much faster than if they were just static particles floating passively.
How much faster?
About 10 times more efficient. They've shown they can take water with dangerous lead levels like 1,000 parts per billion and bring it down below safe drinking limits under 50 ppb in just an hour.
Okay, 10 times faster. That's huge. So looking ahead, it seems like this idea of swarms is really central, like those inchworms.
Definitely. Swarm intelligence, reconfigurability, the ability for a group of bots to change shape, maybe act as a dispersed cloud one moment and a coordinated chain the next. That gives them robustness, adaptability.
Essential for unpredictable places like the human body or polluted water.
Absolutely. But, and this is the big but, while we have these amazing prototypes,
There's always a but. What's the main hurdle to seeing these everywhere?
it really boils down to the grand challenge of control, navigation, and autonomy, especially deep inside the body. Meaning getting truly precise, real-time control and clear imaging of potentially millions of these tiny bots moving dynamically within an opaque, complex, constantly shifting environment like human tissue. That's incredibly hard.
So we need better ways to see and steer them, especially lots of them at once.
Exactly. It requires huge leaps in things like AI for autonomous control and much more sophisticated, non-invasive imaging systems than we currently have widespread access to. That's really the next frontier researchers need to conquer.
So the tiny machines are here, but orchestrating the army, that's the next deep dive. Fascinating stuff.